Okay, so from this week, we'll talk about chapter 6. Actually, chapter 6 is very, it's a topic for one semester. It's a big topic. And we'll talk about the characteristic of the reservoir rock. So we'll talk about the rock property and whether it is the sandstone or the carbonate. Could be a different rock too. And so we'll talk about the characteristic of the reservoir for about 3 weeks. So it's a big topic. So any rock can be served as a reservoir. So reservoir is the formation that contains oil or gas. So the pore should contain the oil or gas. And the pore must be connected to each other so that the oil and gas can be produced. So sandstone or carbonate contain the major known reserve because they have a high porosity and a high permeability. But the hydrocarbon field can also occur in shales and diverse igneous rock and the metamorphic rock. So if it's very fractured. So in case you have a reservoir or the hydrocarbon in economically feasible hydrocarbon reserve in the igneous rock or the metamorphic rock, then that formation should be highly fractured. Or they are very low porosity, so it will be very difficult to produce it economically. So this chapter describes the nature of the hydrocarbon reservoir, and these are the topics that we're gonna cover. And porosity, today we'll talk about porosity mainly. And the next class we'll talk about single phase permeability and also the relationship between porosity and permeability. And then we'll talk about the capillary pressure and the wettability, which is about the rock and oil interface and the oil and water interface, and the relative permeability and the continuity of the reservoir, and the hydrocarbon production method. So this chapter will be very interesting, I hope. So let's talk about the porosity first. So there are many many types of porosity. And the general definition of the porosity is what? The void volume or the pore volume over the total volume, right? And you multiply the 100%. So you express the porosity as a percent number. And there are effective porosity and the ineffective porosity depending on whether the pore is connected or not. So when you have the pore which is closed, so that the pore does not, it may have some oil, but it is not feasible, it's not possible to produce it, then it's a closed pore. And catenary pore and the cul-de-sac pore is the pores connected. And cul-de-sac pore is also called as a dead end pore because its connectivity is only one. So in this, what is the connectivity? So connectivity is the number of connection for one pore to the other pore. So in this case, the connectivity of the dead pore is 1. So in this case, the connectivity is 2, right? So catenary pore is the pore that has the connectivity more than 2, so that the water can flow through it. And depending on the time of the formation of the pore, you can categorize it as primary pore and the secondary pore. So primary pore is those formed during the sedimentation, when the sediment is deposited. So you can imagine that the gravel or the soil particle is transported from the river and they deposited, and then that's the primary pore. And secondary pore is that after the deposition, there could be some compaction by the overburden pressure, and there can be also the geochemical reaction, dissolution and the precipitation of the rock mineral, right? So that's the process for the secondary pore generation. So primary pore, interparticle and intraparticle pores, and it's originated from sedimentation. And the secondary pores are intercrystalline and fenestral, that's from the cementation, and boggy, modic, that's from dissolution of the rock mineral, and fracture is could be from the tectonic forces and the geomechanical forces in the rock formation. So we'll see one by one. First, I think it's primary pore. So first, the interparticle pore is the general pore that we can imagine. It's the same pore that we are talking in the soil. And present in all sediments when initially deposited. So it's not cemented yet. It's just right after when it's deposited. But quickly lost in clays and carbonate. This kind of a pore, interparticle pore, quickly lost in clays and carbonate sand due to the compaction and the cementation. And much of the porosity found in sandstone reserves in preserved primary intergranular porosity. So in sandstone, this kind of interparticle pores are well preserved, but not in the carbonate or the clay stones. And here, this is the scanning electron microscope images of the diatom. Actually, it's a sediment from Ulum Basin. And these are the clay here. These are the clay and silt, very fine sediment. And you can see here, looks like a fossil, right? And there are also one looks like very weird one, and this one too, right? And when you look at this particle, you can see some pores are here, right? And these pores are within the grain, and it's called the intraparticle pores. So if you zoom in, these kind of a micron scale pores within the particle, within the skeletal grains, it's called the intraparticle pores. And this pore is in the scale of the micron. So it also referred to as microporosity. And generally found within the skeletal grains of carbonate sand or silicate diatomaceous sediment. So this is made of silicate. These pictures. So this is called as a diatom. And diatom is formed from the dead body of bacteria or biological microorganism. So this is so it used to be the microorganism. And often it has the cul-de-sac pore, so it has the dead end pore. And because of the compaction and cementation, intraparticle pores are generally absent in carbonate reservoir. So, and the secondary pores secondary pores can be produced by the dissolution. And when it's produced by dissolution, it forms as a modic porosity or boggy porosity. So this kind of a solution-induced porosity is more common in carbonate reservoir than in the sandstone reservoir because the carbonate can be easily dissolved in the acidic water. And modic porosity is fabric selective, there is only grains or only the matrix has been leached out. So only the one grain or the type of the grain has been leached out. And vox are the pores whose boundary cross-cut grains matrix and the earlier cement. So the vox, if the modic is like this kind of a lens type of porosity, so it selectively dissolves a type of grain, one type of grain, or the mineral. But the vox is much more larger. And you can find this kind of solution in this porosity commonly in the carbonate reservoir, dolomite or calcite. And secondary pores caused by cementation is called the intercrystalline pores and refers to pores occurring between the crystal faces of the crystalline rock. And most crystallized limestone generally have negligible porosity, but the crystalline dolomite are often highly porous with a friable, sugary texture. So it's easy to break. And the reason is that the dolomite, during the dolomitization, it causes 13% volume shrinkage. So from the limestone to dolomite, when the limestone is filled with magnesium-rich water, then you have a dolomitization. And during this dolomitization, the volume contracts by about 13%. So that induced the porosity. So here in this picture, like these kind of the blue color showing the intercrystalline pores containing the water. The last major type of the pore is the fracture porosity. And you can see like clear cracks in the rock here. So this kind of a fracture porosity is very important because it can enhance the permeability or productivity of the hydrocarbon. So fractures are caused by failure due to the stress applied to the rock formation. So this kind of a fracture, mostly the fractures are formed by the mechanical failure. So there should be some stress exceeding the strength of the rock. And fractures are rare in unconsolidated, loosely cemented sediments. So this means that you don't see this kind of fractures in soil. Right? So you see the fractures in the cemented the sediments or the consolidated rock. And they may occur in any brittle rock, not only sandstone and limestone, but also shale and igneous metamorphic rocks. And the size of the fracture is much larger than most pores. And fracture, so the existence of the fracture and the frequency or the occurrence of the fracture is very important to evaluate the productivity of the hydrocarbon in the reservoir. So fracture may be recognized from wire logging and seismic data and the production history of the well. And fractures also can be seen by the borehole imaging. So this is the picture from the borehole imaging. And you can see a vertical fracture is developed in this logging result, logging report. And anomalous low velocity also may indicate the fractures. And you can also find the indication of the presence of the fracture from the production history. So high initial production followed by the rapid declines in pressure and the flow rate often indicative of fracture porosity. And the causes of the fracture are three. So there can be three different geologic settings having the fracture. The first is you have a tension and the compression by the tectonic force in this anticline and the syncline here. So but at the anticline, the crest of the anticline, you have a tension. And the bottom, the nadir of the syncline, you have also the tension, and that can create the fractures. And the fracture often occurs adjacent to the fault. So because in the fault, you have a sliding movement. And this sliding movement, during this sliding, it can generate the stress exceeding the strength of the rock, so that you can develop the fractures around the fault. And also the beneath conformity, so 부정합 here, especially in the carbonate, the fracture may be enlarged by the karstic solution. So in this case, the fracture is by the dissolution. So, and the basement rock sometimes serve as a petroleum reserve because the fracture porosity is sufficiently abundant for them to flow. And these reservoirs are commonly dual porosity systems where the solution porosity is formed from the leaching out unstable mineral grade. So let's talk about the basement rock first. So we've been talking about the basement rock. What is basement rock? It's in the next slide. So basement rock is typically described as the rock below a sedimentary platform or cover, or more generally, any rock below sedimentary rocks that are the igneous or metamorphic origin. So basement is mostly composed of the igneous rock or the metamorphic rock. And to be, so rarely, but often the basement also has the hydrocarbon, and it can be produced. Has some economic feasibility of the hydrocarbon production. And in that case, fracture porosity should play a significant role in that. And so when we look at this chart, I think this is a great chart to remember. And most sandstone reservoir, the porosity is proportional to the permeability here, around here. So sandstone has a high porosity, like 20% or 15%, more than 15%. Right? And because of the high porosity, it has high permeability. What about the carbonate rock? Carbonate rock, as we saw just before, it has the porosity by the solution. Right? So it can have the modic and the boggy pore. And these pores are not from depositional process. It's from the secondary process, like the leaching out, right? Or the cementation. So there are many dead-end pore or closed pore in the limestone or the dolomite, this kind of a carbonate formation. So it may have a high porosity, but the pores are not connected well to each other, so that the productivity is, or the permeability is lower than you expect. So here it has a high permeability, high porosity, but the permeability is pretty low, much lower than the sandstone in limestone. And the basement is crystalline rock, igneous rock or metamorphic rock, has very low porosity. So because of the low porosity, it has very low permeability. In some case, this basement rock can be fractured, highly fractured. So then you have dual porosity system. So dual porosity system means that this is the pore size, and this is the occurrence for the pore volume. This is the maybe idealized, simplified figure explaining the dual porosity system. So one pore, you have a large pore system and a small pore system. And this can be frequently found in fractured rock, because in fractured rock, fracture serves as a large pore. Right? This is the fracture. And the matrix should have some pore, right, by itself, because it's made of rock. It's called the pore of the matrix, matrix pore. So the fractured reservoir, even though it has a low porosity, but because of the fracture, it can have the high permeability. 코멘트, 질문. 그죠? So far okay? Good. We've done this one. So the summary, the total porosity is the true porosity, often called. So the pore volume over the total bulk volume. But the porosity does not give any information concerning pore size, their distribution, and their degree of connectivity. And carbonate rock, if we compare the carbonate rock and the sandstone, both can have the porosity of 20%. But carbonate pores are often very unconnected. The connectivity is low, so it may have the dead-end pore or the isolated closed pore, so resulting in its permeability being very much lower than that of the sandstone. We talked about, we've seen this example in the figure. And there are numerous types of porosity: total porosity, connective porosity, effective porosity. So actually, if you have a rock, and if you measure the porosity with the typical method, then you just measure the pore volume, which is connected to each other, right? So you only can measure the effective porosity. Actually, effective porosity is very important because that is directly related to the permeability. Right? The closed pore, you cannot produce, you cannot inject any fluid, or you cannot produce it. So, and primary porosity, secondary porosity, microporosity, intergranular porosity, intragranular porosity, dissolution porosity, vapor porosity, body porosity, right? Bulk porosity. So you can read this through. This is the summary. And then what controls the porosity? We'll talk about the some parameters or conditions that can control the porosity. So initial porosity before before diagenesis. Diagenesis is what? Diagenesis is any process or physical or chemical process that occurs with time. So diagenesis is very long-term process. It can be compaction, or it can be cementation, or dissolution, precipitation. But pre-diagenesis means that before the secondary pore is created, the initial porosity is affected by these four major parameters: grain size, packing, and particle shape, and particle size distribution. These four factors are the affecting the initial porosity. Then the initial porosity can be changed by the secondary controls on porosity, such as compaction and geochemical diagenetic processes. So let's review the one by one, the grain size and the particle shape and etc. The grain size. Okay. Have you ever played with dry clay and sand? When you compact the dry clay and the sand, clay has the specific gravity of 2.7, 2.65, right? And quartz sand also has the similar specific gravity, the density are the same. And when you just pour it, then what will be the porosity between two? Which one is bigger? Porosity bigger. So you have a poor sand, and you have a clay. So using funnel, if you just pouring gently the dry clay and the sand, then with the same maybe mass, Which one will have the high porosity? Clay have much higher porosity. Why? Christine? Sand, no, the specific gravity, so density of grain itself are the same. So clay has 2.7 and sand has 2.65, so both are good. So there are different forces acting on the particles, particle to particle. In the case of sand, you have a large particle size, right? So gravitational force is dominant. But in the case of clay, the particle size is very small comparing to its weight. So electrostatic force can overwhelm or it can overact over the gravitational load because the particle size is small. So when you just pour it, whether it is in water or air, the porosity here will be about like 0.7, 0.8. And here the sand, the maximum porosity you can reach is probably 0.42, maybe 45%. And here it can be larger than 60%. From my experience. Right? So the difference is that clay has electrostatic force and sand has only the gravitational force, which is the major force. And the difference is from the particle size. Right? Clay can also have a negative charge, and also sand can have a negative charge on the surfaces, but its particle size is much larger, so the gravitational force is like outwin. It's winning against this electrostatic force. So it means that as the surface relative force are proportional to the surface area of the grain, so specific surface area is very important. And what is specific surface area? I think we talked about this, right? The surface area of the grain over unit volume or maybe unit mass. Right? So meter square per gram or meter square per meter cubic. Right? And specific surface area is inversely proportional to grain size. So as the grain size decreases and the surface area increases, that means that then you have much larger, you have increase in surface area, surface relative force as the grain size decreases. So force increases with a decrease in grain size, then more stable at the high porosity. So again, when all other factors are equal, coarse grain will be stabilized at the lower porosity or higher porosity than the same weight of the finer grain. Is it lower or higher? Confusing. Oh, lower. Good. It was 50% chance, right? So, I think we talked about this. And I think this figure is great example showing you just the concept just before. So as the grain size decreases, you have an increase in porosity. Right? For the rounded grain, especially the particle sizes become less than 100 micron, you have a rapid increase with a decrease in grain size. So at grain size lower than 100 micron, the increase in porosity becomes significant. And for some recent sediment, porosities can be up to 80%, 0.8. So this can be quite high. As the grain size increases more than 100 micron, the frictional forces decreases and the porosity decreases. So as you go this direction, frictional force or your electrostatic force becomes insignificant comparing to the gravitational force. So here, gravitation controls, and here, electrostatic, or the friction, surface relative force controls. And they say it's 100 micron, but we know that the more specific number from the unified soil classification system. What is the particle size threshold, particle size between the fine and the coarse grain? What sieve do we use? 200 number. And what's the opening size of the 200 sieve, number 200 sieve? That's number 4. Number 200 sieve has the opening size of 너무 오래됐죠? It's 75 micrometer. Right? So 75 micrometer, we use that number to differentiate the fine grain soil and the coarse grain soil. Right? And fine grain soil has heavy influence by this surface relative force. So this is very, in some sense, it's very obvious that we have this kind of a significant trend in this region. The grain size diameter less than 100 micrometer. And the porosity, and you can see as you go to this direction, it approaches to the limit of the random packing. And the random packing can have the 0.4, so 40% porosity when it's the rounded grain. And this is independent of grain size. So you have always the limit, the porosity limit. 질문? Question? Comment? No? The second control on the porosity is the grain packing. So if we assume a uniform size sphere, depending on the packing, you may have different porosity. Right? So which one is the largest one? The simple cubic packing has the largest porosity, 48% about. So this is the simple cubic packing, right? This one. And the smallest one is what? Which one is it? Rhombohedral, right? Rhombohedral is this one. And the random packing is the lower limit is about 0.4, the 40%. But depending on the packing, you may have a different porosity. And the grain shape. So the grain shape can be spherical or non-spherical. And non-spherical grains will have a lower void ratio or a higher void ratio. So high porosity or low porosity comparing to the round shape. High porosity. So non-spherical grains have the porosities larger than those for the spheres. So if it's angular, the porosity for more angular grain is larger than those that are subspherical, and I think this shows also the effect of grain shape. Sphere, if it's random packing, 40%, and cube, 42.5%, and cylinder, 43%, and disc, 45%. And actually, in geotechnical engineering, we also concern about the particle shape these days in the strength and the mechanical behavior. And we can quantify the grain shape with two parameters. One is sphericity, and it's defined by the diameter of the largest inscribed sphere related to the diameter of the smallest circumscribed sphere. So if this thick line is the grain shape, then largest maximum inscribed sphere will be this one. Right? So R max inscribing. And the circumscribing, the minimum diameter is the one that is enveloping this particle, right? This one. The ratio between this and this gives you the sphericity. So if it's perfect round, then sphericity should be 1. Right? And as you go down, so as the sphericity decreases, it becomes more like platy. More like a plate particle. So it's also called as eccentricity or platiness. And the second one is roundness, as you can see here. And it's also called as our angularity. So the average radius of the curvature of the surface features related to the radius of the maximum sphere that can be inscribed in the particle. So as you go to this direction, you can see here is more angular and this is more round, right? Angular and more round. And there's a particle regularity, which is suggested by these two guys, Crumbain and Sloss. And so regularity is just the mean of these two parameters, roundness and the sphericity. So then we can test the maximum porosity and the minimum porosity for different particle shape, right? And also with the similar the particle size. Then this is the figure. I think it's a really great work. And void ratio is a void ratio. E max is the maximum void ratio, and E min is the minimum void ratio. And void ratio is related to the porosity by this equation. So you have a 1-to-1 relation. So large void ratio means the large porosity. Right? So as the roundness increases, maximum porosity decreases, and also the minimum porosity decreases. And sphericity also has the same tendency. It means that as the particle becomes angular and platy, then you have a larger void ratio or larger porosity. And so far, any question? Okay. So the last one is the grain size distribution. And the real rocks contain a distribution of grain size. Often the grain size distribution is multimodal. And so size distribution affects the porosity. Let's consider this a mixture of two grains. So one with very large and one with very small. And then if we mix these two, there are two mechanisms at work. First is when the grains are made of, the skeleton is made of the large grain, then small grain will fill up the void. Right? So that mixing these two type of particle will decrease the porosity. Right? Comparing to the case that you have only one type of particle. And the second is when the small one fraction is much more than the larger one. So the grains are made of, skeleton is made of small particle. Then you're mixing this large particle, then what happens? This volume is replaced by this large particle. Right? So anytime if you mix two different size particle, then it's good for porosity. It's good for decreasing the porosity. Right? But here's why. Because this is just a one grain. So before replacing it, there were some pores, right, between the small particle. So these two mechanisms works here, and then you have this figure. When the diameter ratio is 2 to 1, so you have a 6 and 3, so 3 diameter and 6, and here and 50 to 5, so 1 to 10, right? 10 and 1, and this is the volume fraction. Here x-axis is the volume fraction. So when the coarse grain is 100%, when the fine grain is 100%, and as you go to center, it's a 50-50, right? 50. And these dots are showing the final porosity after the mixture, after you mixing it thoroughly. And you can see that always it's lower than its pure porosity. And this line is the theoretical line. And as the particle size becomes more larger, then this the real porosity value approaches to the theoretical line. And the minimum void ratio here, or the minimum porosity, is always happens in around 22 and 30% of the fine fraction. So it's good to have a different size in your soil or the sediment. That's gonna decrease the porosity. I don't know whether it's good, but it's good in terms of decreasing the porosity. So that's why in soil mechanics, we categorize the soil as well-distributed soil, or the well-grained soil, or poorly grained soil, right? If it's well-grained soil, then you have also good characteristic in the mechanical strength. And if it's poorly graded soil, then you have a good characteristic in the hydraulic conductivity. So there's a pros and cons. Okay. The secondary controls on porosity is by the compaction and dilation. And so there are two categories, the mechanical process and the geochemical process. Mechanical process is including the stress, compaction, class deformation, brittle deformation, fracture evolution. And geochemical process includes dissolution, precipitation, volume reduction upon the mineral composition changes. And this shows the porosity reduction with overburden pressure. So this is the porosity when you take out the sample. So the sample is cored from the drilling hole, from the formation that you are interested in. And then the stress is all relieved, right? So that's the porosity here when the stress is zero. And as you recover and recreate the stress over the stress, you have a decrease in porosity, right? So you can see that it can decrease to 5%. I don't know what the rock is. I think it's a sandstone with initial porosity of 19%. And under the overburden pressure of 5,000 psi, you have a decrease in porosity by 5%. Then how can we measure the porosity? So let's talk about the measurement method of the porosity. There are three ways: direct method, directly from cores, and indirectly from geophysical logs. And we've talked about these two in chapter 3. And today we'll talk about the direct measurement method from the cores. So main reason for cutting a core is to measure the petrophysical properties of reservoir, including porosity. And porosity may be measured in the laboratory using several methods. For homogeneous rock, like vein sandstone, samples only small volume, 30 millimeter cubic, also may be cut or chipped from the core. If it's heterogeneous reservoir, including many limestone, analysis of whole core sample is generally necessary. So in case of homogeneous rock, you just need a small sample as a REV, but in case of heterogeneous rock, then you need a larger sample to have the REV. So again, the definition of the porosity here, and then, so to get the porosity, we need to know the volume, bulk volume, right? The bulk volume of the sample, and the grain volume. Or we can just measure the pore volume and the bulk volume. So, and this measures the total porosity. And what it does is the direct measurement is that you have a rock core, and you just grind it. So first you measure the bulk volume, and then you grind it, and then measure the grain volume. Maybe using the picrometer. You can just pour it in the graduated cylinder, then changing fluid volume will give you the grain volume, right? So this is rarely used on rock because the solid volume can be measured if the rock is totally disaggregated. And then after that, it cannot be used for any further petrophysical studies. So you're wasting a core. So you consume one core for that. And imbibition method is the typical method. You just immerse it in a wetting fluid, like water, and wait until it's fully saturated. And then you wait before and after the imbibition. And then the density of the fluid, water, is generally known. So difference in weight gives you the pore volume. Right? Bulk volume is measured using calipers, assuming the cylindrical shape, or Archimedes method, or by fluid displacement using the saturated sample. We'll talk about this one soon. And pore volume and bulk volume can be used to calculate the connective porosity in this case, right? Because we are measuring the pore volume by injecting or wetting the pores with the water. The water will just penetrate into the pore which is connected. So this will capture the connective porosity, and connective porosity is, in other words, the effective porosity. So the example is that here, you have a dry sample that is mass is 20 grams, and you immerse it in water, and then you take out the sample which is saturated, and maybe you just swipe it with the water, the paper towel, and then you measure it. Then it will give you the saturated mass. Saturated mass here is 22.5 grams. Then how do we measure the bulk volume if it's irregular shape? When it's saturated, you just immerse it in the graduated cylinder. Sorry, it's not graduated cylinder. Sorry. Then just hanging in the immerse in water and measure the wet mass, submerged mass. And then weight of the water displaced. Give you the bulk volume. Right? Does it make sense? So how much is the bulk volume? If the the water density is 1 gram per milliliter, the bulk volume will be 9.9 cc, or the 1 gram per cc. Then how much is the porosity? So you have a bulk volume here, and you have a pore volume from these two values. How much is the pore volume? You can subtract the dry mass from the saturated mass, right? 22.5 minus 20 grams, so 2.5 cc or milliliter. Right? So this is the pore volume, then the porosity is 2.5 divided by 9.9. So that's going to be around 25%, right? 25.3%. Right? So this is the imbibition method. 질문 혹시? So this method is you have a saturated sample and you just measure the mass within the water, right? So to consider the buoyancy force, submerged mass. Okay, the next method is the gas expansion method. This is a typical method used in the rock mechanics or the geology. So you have one chamber that contains the rock sample, but you should know the volume of this chamber. Right? So the volume of this chamber is known, and when you put the rock, and also you can measure the pressure of this chamber inside. Right? So you have a P1, and the vapor or the gas volume here is the V1 minus Vs. Right? Here the Vs is the solid volume of this rock. And then this chamber is connected to another chamber with known volume and known pressure. So here the P2 and the volume is V2. And then just open the valve and you wait until the pressure is equilibrated under isothermal condition. So here to have the valid boils low, then it should be isothermal condition. So the temperature should be the same, should stay constant. Isothermal condition. Then you have a P3 here. Then what will be the final equation? P1 times V1 minus Vs plus P2 times V2 is P3 times the total volume, right? The sum of two chamber volume, right? V1 plus V2 minus V3, Vs. And this also measures the connective porosity or the effective porosity because the gas cannot penetrate to the closed pore. And any gas can be used, but the helium is commonly used. So let's solve the one example. Right? V1 times, V1 minus Vs times P1 plus V2 P P2 equals P1 times P3. But here the P1 is 0, so it becomes very handy, right? P2 this will be, you can put it into left side, and P1, P2 times P3 minus P2, P2, right? So this P, oh, sorry. So the solid volume, the grain volume will be 1 over P3 times minus so you can plug the numbers here, B1, you know the B1 and B2, and P3 and B2, right? So then you get the grain volume at 14.34 milliliter. Okay, so then this gives you the grain volume, not the bulk volume, right? So you can measure the bulk volume with different methods. First one is just assuming the rock is perfectly cylinder. So then you have to have a perfect shaped core. Generally, the coring tool give you a perfect shape. You just need to cut it in at very flat, right? But if you have highly porous rock, then you may have irregular shape with rough surfaces. Sometimes the surface could be very rough because the grain is large, right? And sometimes if you have a boggy structure, then here is empty, and here is empty, and also here is empty, right? So then it's quite difficult to have an accurate measurement for the bulk volume. So then, what do we use? We can have a fluid displacement. This is actually the same. So you have a graduated cylinder, and you put the rock core, right? And then rock core is here, and then you have an increase in water volume or fluid volume, then this gives you the bulk volume. And before, people used the mercury because mercury doesn't penetrate to the pores. But the mercury, they don't use it anymore because once you use it for this bulk volume, you cannot use this core anymore. It's difficult to clean out all the mercury. And people use the water with the saturated core. And the other method is the Archimedes method. It's basically the same that we just solved it in the, I think the first example. Sample, you measure it in the air, the dry sample, and after they're fully saturated, you also measure it in the water. So you weigh the dry mass, and after that you fully saturate with the formation brine, whose density is known. And saturated sample is then weighed, suspended in air, and while they were suspended in the fluid. And this allows the bulk volume of any irregular shape to be found accurately. So then you can read it through. And there are some few sources of significant error in this method. Provide no fluid drain from plug while it's weighed in air. And the most difficult part is judging how much excess fluid to remove from the surface of the plug. So it's difficult to, when you immerse it in the water, let's imagine, then you take it out, you have a water dripping out, right? Then until when will you wait, right? That will be the difficult part when you measure the saturated mass. And also it will be very difficult when you have a boggy limestone too. Is that all? Yep. So that's all for today. Any question for porosity? So we talked about today mostly of the porosity. And The next class we'll talk about the permeability of the rock.